So welcome to everybody. My name's Paul Dowling, and I think we'll make a start. So we've got a good turnout. So welcome to this Quantum Computing for Finance session. I'd love to welcome Dr. Román Orús. I'll say a bit more about him in a moment. So first of all, I'd like to thank Association Quantum for their sponsorship of the event. Just to mention that the next event, which is on March the 26th, is Quantum Computing for Agriculture Efficiency and Sustainability. So that should be very interesting. I'll mention that again at the end of the event. So I'm very honored indeed to be introducing Dr. Román Orús, who is Ikerbasque Research Professor at the Donostia International Physics Center in San Sebastián in Spain. And that's quite a mouthful. He's had a long and varied involvement with academia as a research fellow at universities across the world. And I'm very envious with all the places you've been to, Dr. Orús. He's also is president of the Spanish group on quantum information at the Spanish Royal Society of Physics. Román is also the co-founder and CSO at Multiverse Computing. He will make a non-technical overview of the quantum computing, about how it can be applied to the financial industry, and should be very interesting. So, Dr. Orús, I'm going to stop my share and you can share your slides and start the presentation. Oh, I should just say that please put questions in Q&A rather than chat. And what we'll do is we'll have a fairly fulsome Q&A session at the end. Thank you very much.
Excellent. So thanks a lot, Paul. Let me just share my screen. Actually, this one. Okay. So excellent. So yes, I was saying thanks a lot, Paul. Thanks a lot also to for the very nice presentation. Thanks a lot also to the organizers for for inviting me to give a talk in this series of meetings. I'm really, I'm very happy to be here and really deeply honored. So so today I wanna tell you about quantum computing for finance. Now this topic is very broad indeed. One could go into many technical details. My approach here today is to be, well, at least there's going to be a part, at least that is going to be non-technical, and I want to give an overview of why, quantum computing is important for financial problems and why finance is going to be one of the first applications of an actual quantum computer. Eventually, I will explain you 3 or 4 problems a little bit more in detail, in which we've been working on for the past couple of years. Multiverse computing, they have to do with topics such as portfolio optimization and so on. And then, for those of you there in the audience that have a little bit more of technical background, that do quantitative finance, maybe know a bit about machine learning and so on. I think that's also going to be interesting for you. And yeah, and don't hesitate to write questions in the chat or the question and answer. I will be super happy to answer them. Okay, let's move on. So first of all, let's locate us a little bit. So Multiverse is located in San Sebastián. That's where I'm at the moment. For those of you that don't know where San Sebastián is, this is in Spain. It's actually the closest city in Spain, a big city in Spain to France. We are only 20 kilometers from the border. So we are the closest thing to being friends without being a French, actually. We are over there. It's a nice place for holidays and also for surfing, for, there are also nice restaurants, as we were discussing just 5 minutes ago. So you are very welcome to come and visit whenever you can travel again. All right. It's definitely an interesting place. There is not just holiday people. There are also interesting science going on, and also, scientific research centers such as the DIPC, and also quantum startups such as Multiverse. All right. Let me give you a couple of words about Multiverse. computing. This is the startup that we built around the idea of applying quantum computing for finance. We are actually the world leaders in the pack on applications of quantum computing for financial problems. We have 2 offices at the moment, headquarters in San Sebastián in Spain. We have another office in Toronto in Canada. We are opening very soon, actually this month, another office in Paris, in France. And this year we expect also to be in Germany, in Munich. And you know, we have agreements with many people. We've been supported by people such as local governments, also accelerators from Toronto, such as the Creative Destruction Lab, also universities and so on. And yeah, we are very happy. I invite you to have a look at our website. It's full of interesting stuff. We also have been doing some interesting work. This is why we have been highlighted actually in some interesting places, such as reports from the Boston Consulting Group, from McKinsey, also reports from IBM. Recently, we also showed up in The Economist, also in Forbes. And you know, these are journals that have to do with finance. So it probably means that we are doing something interesting. Okay. And yeah, I also invite you to have a look at this if you want. All the information is on our website. All right. So let's move on. So this talk is about quantum computing for finance. Before talking about finance, we need to start talking about quantum computing. That's the reason why we are here. So probably, you know, if you follow these seminars, you already have an idea of why quantum computers are important. In any case, let me just revise it once again, because I think it's interesting and also important to you know, to have a common background on why we are all here. So what is quantum computing? So quantum computing is about using quantum mechanics to do calculations. So, you know, quantum mechanics are the laws of physics that rule the physical world and the universe at very small scales. Okay, so the rules of every day, they are dictated by classical physics, but when you go to atoms, molecules, and so on, elementary particles, so classical physics doesn't work anymore, and we need to use quantum mechanics. It's a different world. Things are very counterintuitive at that scale. And in practice, in physics, we realize that one can use these laws of nature and the universe to codify information and process it in more efficient ways. That's the idea of quantum computing. To use quantum mechanics to do calculations that otherwise will be intractable, simply because we can process information in different ways. Nowadays, we start having some quantum processors in the lab. So for many years, this was almost like a university experiment. It was in research departments, research labs, mainly because, you know, quantum systems, they are very delicate, they decay very quickly, and we didn't have the level of control to actually manipulate these systems until very recently. But nowadays, we are already starting to have quantum processors out there, and that's the reason why quantum computing is exploding, you know, in the practical sense. So, for instance, we have quantum annealers, such as a machine that is built by a company called D-Wave. This is a type of quantum computer that is built only with one purpose, which is to optimize. Okay, it's solving just one particular type of problem. There are also something called universal quantum processors that are based on the quantum gate model. This, if you heard about the IBM quantum computer, the quantum computers by Google, also by Rigetti, also Alibaba, Baidu, these are the examples that I'm showing here. All these are gate-based quantum computers. They are the closest thing to what we have in mind about a computer that is built on logical gates. So this will be the analog in the quantum case. This list is by no means exhaustive. There are more models. There are more ways of building quantum computers. And the idea is that quantum processors are evolving every day. So as we speak, there are people working on improving the performance, accuracy, and size of quantum computers by trying to add more qubits, reducing the noise, and so on. So this is a technology that is evolving very quickly, and we are going to find it sooner than later. What's the idea behind quantum computing? Well, you know, we want to use quantum systems to codify information. For classical systems, we codify information using bits. These are variables that can be in one of two values, no? So they can be either in 0 or in 1, all right? And then a classical computer is just a huge system that is processing all these strings of zeros and ones. Now, if we go to a quantum system, it turns out that already at the level of this fundamental representation of information, we have something that is far more powerful. This is the quantum bit or the qubit. This is the fundamental unit of quantum information, and it's not a binary variable that can be either in 0 or in 1. It's actually something that we call a vector. You can imagine that it's an arrow that is pointing in some direction, and therefore it can be in states such as in 0 or in 1, or it can be in any other state, such as, for instance, a sum of 0 and 1, as I'm showing here, and many others. All right. This is already telling you that already at the level of 1 qubit, there is an infinite amount of extra information that you could codify with respect to a classical machine. All right, that is built on bits. There are more ways of seeing that quantum computers are very useful. So also, there is something called quantum parallelism that is, something that actually makes a difference. So this is better explained with an example. Imagine that you have many keys, like 20 keys, and you want to learn which one is the one that opens a lock. All right. So in a standard computer that is using just one CPU, the strategy will be, okay, let's try all the keys one by one until I hit the one that works. All right. Now, if instead of having just a normal CPU, you had a cluster, okay, or a supercomputing cluster with many CPUs, like a high-performance computing device or something, then the strategy will be very simple. Let's just try all the keys in parallel to many different copies of the lock. All right, and then there's going to be one that is going to work, and I'm going to solve the problem in just one step. But I'm going to use a huge amount of memory because I need all these processors. Okay, this is the idea of parallel computing. Well, quantum computing can be seen as something that is bringing the best of both worlds. We are going to be trying all the keys in parallel, but not in many locks, but in only one lock. So we pick up the lock and put it in superposition, in quantum superposition, and then we try all the keys in parallel at the same time in only one processor. Okay, this is something that is not possible in classical computing, but it's possible in quantum computing because of something called quantum superposition, and it's actually one of the reasons why quantum computers are much more efficient in processing information. You already see that one can do things here that in a classical computer are simply impossible to do. Now, when you put this on asteroids and work out the consequences, there are clever people that come with very clever algorithms. This is, I think, the most paradigmatic and typical example. It's the Shor's factoring algorithm. It's an algorithm for factoring integer numbers into their prime factorization. And here is an example that is very dramatic, which is, imagine that you want to factor a number. So finding the prime factors of, say, for instance, 15 is very easy. It's 5 times 3. But if you have a number with 617 digits, such as the ones that we are using nowadays in cryptography, so in RSA crypto systems, for instance, these are used in practice. The best classical algorithm for finding this factorization actually it takes of the order of 10 to the 34 steps. And when you put it into numbers in terms of, okay, how much time is this going to take for a typical computer, or even for the best computer that we have nowadays, it's going to take of the order of 300 trillion years, which is insanely large. Okay, so this is much more than the age of the universe many times. So there is a way, okay, that one can solve this problem with this algorithm. However, using a quantum computer, if we had a sufficiently powerful quantum computer, one could run Shor's quantum factoring algorithm, and it will take of the order of 10 seconds. Actually, the estimations here change every now and then. I saw last week, there was another paper estimating how many qubits and how much time do you need to factor an RSA number. The estimations are going down and down because of more and more clever tricks. But it gives you the idea that there are two different paradigms here. So in classical computing, we can just not solve this problem with the tools that we have nowadays. In quantum computing, we can, okay? We have an algorithm that could solve this problem very efficiently. So it's a completely different way of thinking about problems. Now there are problems that until now we just didn't think about them because we thought that, okay, this is impossible to solve. And now, once we start having sufficiently powerful quantum computers, we need to pick up those problems from from the closet once again and start thinking about them, because many of them are going to be solvable, right? And this is an example. Good. Let's move on. This is a nice example of an application of a quantum computer. Actually, it was one of the first practical applications of quantum computing into a real life problem. I think this was the people from Volkswagen together with D-Wave, which is this Canadian company building quantum annealers. They used the quantum computer to optimize in real time the traffic in big cities. In particular, they did a couple of pilot projects, one in Beijing, another one in Barcelona, and I think that recently they did another one in another European city, but I don't remember which one. And as a proof of concept, this was very successful. In Beijing, they were optimizing the routes of the taxis from the city center, from downtown to the airport. Of course, if all the taxis follow the same route, there's going to be a traffic jam. So, it has to be optimized on the fly in order to minimize the traffic jams. And this was done using D-Wave. And also in Barcelona to predict the demand of taxis based on actually cell phone data, okay, depending on GPS data from the cell phones of people. This was done by Volkswagen, and I think it's it's already quite old in the sense that it's 5-6 years old. No, yeah, 5-year-old more or less. But I still find that this is a very interesting and nice proof of concept of what quantum computers could do for you once we start using them into real life problems. All right. Now, quantum computers are going to be useful soon. Of course, it's going to depend on the application that we want to solve and the problem that we want to solve. That we are going to be able to use quantum computers sooner or later. All right. And also the impact of these applications is going to be higher or lower. So this is a good summary. This is not by me, it's by Gartner, this company that they make these magic quadrants. And in the horizontal axis, you have the expected time to market of several algorithms. And in the vertical axis, you have the business impact of the algorithms. And here you can see some interesting things. You can see that there are some algorithms that are going to come at in the long term. An example is the factorization algorithm, the one that I was explaining just 5 minutes ago. Also, molecular simulations and so on. But however, there are some applications that are going to come pretty soon. All right, this is around medium term. Now, some of these applications are going to be of high impact, okay, or medium impact. So for instance, something that is going to come pretty soon is the application of quantum computers to solve optimization problems. So this quantum optimization is something that, optimization problems show up every day. And I think that in this sense, these quantum annealing processors by D-Wave are starting to have some business value in real life situations. And it's going to be one of those applications that comes earlier. Now, the other application that is going to come relatively soon, and this one has a large impact, is quantum machine learning. So it's all the quantum part of artificial intelligence, quantum machine learning, quantum neural networks, quantum classifiers, all these sort of algorithms, of which support vector machines. It's just a particular type of algorithm. This is going to come relatively soon. And of course, the amount of applications is huge, so the impact is very large. Now, the reason why this is going to come relatively soon is because for these algorithms to run, one doesn't need very powerful quantum processors. Actually, with small, noisy, intermediate scale quantum processors, such as the ones that we are building nowadays, one can already start doing non-trivial things with quantum machine learning algorithms. There are even quantum classifiers that are using one single qubit, and they work, okay? And they provide solutions that, give a precision and an accuracy of classifications that is very hard to get with classical machine learning, such as neural networks, for instance. And this is very promising, all right? So these two research directions are gonna produce results early, quantum machine learning, quantum optimization. Now, Gartner also is expecting that the business impact of quantum computing is gonna grow exponentially in time in the next years. I mean, as an example, in the last 3 years, and I think that this is actually already outdated, there were more than 250 new startups worldwide, probably more than this. I may be underestimating this number. And by 2023, the global quantum technology market is expected to reach $13.3 billion US. But probably, perhaps if somebody read this calculation nowadays, maybe it will be higher, okay? So, you know, quantum computing is here, it's no longer science fiction, it's gonna happen, and in my opinion, it's gonna happen sooner than later. All right, so why are quantum computers useful? What can we use these machines for? Well, there are many different applications. Material science, of course, because materials, at the end of the day, they are made of atoms and molecules. And these are quantum systems. We need quantum mechanics to describe them. And of course, if they are built on the rules of quantum mechanics, then we better use quantum computers to describe them, because otherwise we are not going to be able to predict many of their properties. So materials, we are already starting to have some very interesting materials with quantum topological properties of quantum matter and so on. This is a very important field of technology. In finance, okay, we'll go into details later. In chemistry, of course, chemistry reactions is also quantum physics applied into into some specific problems. So for many chemical problems, we need quantum computers, all right, to solve more efficient solutions for optimization. And here, there are going to be applications in logistics, in the supply chain, in essentially anything that you can think about. In machine learning, of course, anything that has to do with artificial intelligence and standard machine learning algorithms, they can be improved both in efficiency and precision using quantum computing. And I always say that the most interesting application of quantum computers is still to be discovered. So we can apply quantum computers essentially for whatever we can imagine, but I like to say this because we still don't know what's going to be the key application of a quantum computer. We know what we can apply quantum computers for the problems that we know today, but we will not know for what is really useful this machine until we don't have it in the lab. All right. This is like, I like to compare this situation with classical computers. So with the standard computers, this will be like, you go to the 1930s and go to Alan Turing, who was devising a classical computer, the first Turing machine, no? And you go and tell him that the best application or the most important application of the machine that he's building is going to be Twitter. All right. He will probably tell you, well, what the hell is Twitter? No, it's a social network for connectivity and so on. And it's something that he never had in mind. Okay, he wanted to build that machine to crack crypto systems. He never thought about social networks. So I think that with quantum computing is going to happen something very similar. We know what the computer is useful for, and we have a motivation to build it today for all these problems. But the most important application of a quantum computer, we still don't know it. We will know it once we have the machine and we've been using it for a while. Okay. Excellent. In any case, in this talk, I want to talk about finance. Who is interested in applying quantum computing for finance? Well, anybody that is dealing with financial markets and, manipulating money. So banks, of course, central banks that put the regulations on the banks and also on economies, finance departments of very big companies and corporations, rating agencies, also insurance companies, I forgot to mention also here, regulators, tax offices for detecting fraud, anything that has to do with money, essentially, applies algorithm for in some way or another, and they are going to be users of quantum computing eventually. Now, why do we want to use quantum computing for finance? Well, because finance itself it's full of very hard mathematical problems. Finance is a discipline of science, actually. There is even the Nobel Prize in Economy that is strongly mathematical and very, very complex. All right. So finance has to do with the flows of money and the laws of the market, and this is a very complex system. All right. There is a huge number of variables. They are very strongly correlated. All right. So it's really a complex system of the type that we deal with in physics. It could be compared to a very chaotic and random quantum material, but it's even worse in some situations. It's extremely difficult to predict precisely because all the equations ruling finance, they are very, very complicated and the system is really chaotic, all right? So there is no surprise when, when one thinks about this and realizes that, well, there is a strong mathematical component behind finance, and it's full of optimization problems. It's full of things such as Monte Carlo sampling, all right? It's full of machine learning, partial differential equations, deep learning, and so on. So it's a strongly mathematical. There are also many computer science algorithms working, trying to solve strong and hard financial problems, all right? And this is exactly the place where quantum computers are good for dealing with systems with many variables that are very highly correlated, they are very chaotic, that they have to do with very hard mathematical problems. So that's exactly the place where quantum computers are good, all right? Now in finance, there are all these people working on quantitative finance. They are called quants, and these are the people that are dealing with computer programs to predict the market, to predict the trends, to do trading, and so on. All these are very hard problems, and for all these people, doing quantum computing is going to be useful. And of course, in finance, if you have a speed up, in practice, it means that you are better than your competitor and you can get the calculations better and also faster. It implies more savings for the company. So there is this trade-off that time is money. And of course, this suddenly becomes very valuable from the industry point of view. All right. So what are the types of questions that we can deal with in finance? So a typical question could be this one: how should be the composition of a portfolio of assets, all right? And how should I change it according to the rules of the market? So here the typical tool is optimization models. How could I detect opportunities in trading assets in the market? Okay, here people do a lot of machine learning nowadays. And also, how could I estimate the risk of a company or the risk of a portfolio or the risk of the whole economy, for instance? Here, the typical tool is Monte Carlo method. So essentially, these three families of methods, they are used very widely in finance, okay? Now, in all three of them, we can provide something with quantum computing. We can do quantum optimization, we can do quantum machine learning, and we can also do something called quantum enhanced Monte Carlo that is based on an algorithm called quantum amplitude estimation. So we can speed up also Monte Carlo simulations using quantum computers. Now, typical problems for quantum optimization. Well, portfolio optimization is the canonical problem in finance. Credit scoring for a bank, determining whether they are going to give you a loan or not, okay, or an insurance. No? Finding arbitrage opportunities. It's also a typical problem in finance. When there are cycles. This is about detecting cycles in the market, such that by trading assets, such that at the end of the cycle, you actually have a net return. This is very difficult to detect. And one can also do it using optimization. Also crash prediction, I will talk about that. For quantum machine learning, well, essentially all applications of machine learning nowadays in finance. Fraud detection, determining whether a given transaction is fraudulent or not. This is a classifier, okay? And one can improve it with quantum computing, classifiers, PCAs, principal component analysis, regression for predicting the trends of the market, neural networks, variational quantum eigensolvers and autoencoders. These are specific algorithms for quantum, for improving also quantum optimization, but they are based on quantum machine learning. And also anything that has to do with Monte Carlo can be improved, okay? Monte Carlo sampling, one can do pricing of options and derivatives. This is a very complicated problem in finance, and it has a huge market. Also, as I was saying, estimating the risk of a portfolio, of a company, of the economy. This is typically done using Monte Carlo sampling. We can improve this also using quantum computing. All right. Now, for quantum optimization, nowadays, I would say that there are three main strategies. There is one based on something called quantum annealing, and this is using this type of processors that are built only for solving optimization problems. Here, the typical processor, well, the canonical example is a processor that is being built by D-Wave. D-Wave is a company in Vancouver, in Canada, that they are building a quantum annealing processor, all right, that it's only built for solving optimization problems. Nevertheless, also with the quantum processors that other people are building, such as Google or IBM or Rigetti, that they are based on the gate model of quantum computing, and they are called also universal quantum processors. One can also solve optimization problems. There are two famous algorithms. One is called quantum approximate optimization algorithm, or QAGWA. The other is called variational quantum eigensolvers, or VQE. One can also use these two options. They are good. However, since these universal processors, they are still limited in size, the typical problems that one can fit into these processors is still a bit limited, all right? Good. There is also something called quantum-inspired optimization. I would like to say a couple of words about this. So quantum-inspired optimization is a family of methods that is inspired by how quantum computing works, okay? But they are not quantum. They run on classical machines. That's why they are called quantum-inspired and not quantum, all right? They run on classical machines and they are inspired by how quantum computer works, all right? There are different options also here. So for instance, Fujitsu has a processor also built for optimization that is called the digital annealer. It's like an emulation of a quantum annealer. Microsoft has a toolbox for quantum-inspired optimization as well. And there is also a tool in that is jumping to industry now, and it's coming from physics, called tensor networks, that we are using at Multiverse in particular, and we are world experts. That is also based on descriptions of very complicated quantum states in terms of a mathematical object that is called a tensor networks. And these are new methods that are making the transition from physics to industry. Now we know how to solve very complex optimization problems with them, also how to improve existing machine learning algorithms using tensor networks. We are testing that. Also Google is doing that. They are working really well. They are faster, better, and more precise than standard machine learning techniques, such as, for instance, deep learning. And we think that this is very promising. So I'm mentioning these quantum-inspired methods also because I think they are important. And in my opinion, they are the natural middle step towards quantum computing, in particular for those people that come from a more traditional or classical computing background. All right. Let's move on. Let me show you the typical example of an optimization problem in finance and how we can solve it with a quantum computer. So this is portfolio optimization. The problem is very simple. I have a number of assets. So bonds, cash, stocks, gold, and real estate. It could also be apples, oranges, bananas, and I don't know, and whatever you want. And I want to know what has to be the composition of my portfolio, okay, of assets every day, taking into account how the price of each asset is going every day up and down in order to maximize the return in a given time period. So say I want to invest in a portfolio and I'm going to be trading every day and I want to maximize the return the day I retire from physics, okay? And then I can go to the beach in San Sebastián. No? So I want to have as much money as possible, so I want to maximize this return. This is a typical optimization problem, all right? How has to be the composition of your portfolio every day to maximize this quantity? One can put this in mathematics. Don't be scared by the equations. The idea is that we need to maximize something. It's the return. Mathematically, we write it like this. It's the sum of the forecasted return every day for every asset multiplied by how much do I have of every asset, okay? And we have to minimize another quantity, which is the risk, which mathematically is expressed in, well, it has this expression, okay? It has to do with how much I have, again, of every asset, which are these omegas. And then there is something here in the middle that is called the covariance matrix, okay? That has to do with the fluctuations in the price. So the bigger the fluctuations, the more risky is gonna be the investment. So I need to maximize the return and minimize the risk at the same time. And on top of that, perhaps add some extra constraints, okay? So for instance, that I have a fixed amount of money to invest, okay? Or for instance, that I'm not going to invest more than a cap on every asset so that I can diversify. This is also a typical constraint. So one can put all this into mathematics and, write down an optimization problem. I have to write down a function that I have to optimize. This is how the function looks like. Again, don't be scared by the mathematics. This is a complicated equation that we have to find the minimum of, all right? Or in this case, exactly the minimum. So there is the return, there is the risk, and then there is something here that has to do with the transaction cost, because every time I change the proportion of the assets that I have, the bank is gonna, there is some transaction cost associated to that. All right, that's how banks make money also. And there are also other constraints, such as total number of assets is gonna be a constant. Now, we have to minimize this equation, and this is an extremely hard problem for classical computers. Why? Well, because if we discretize it, it means if we write the variables in terms of bits, and it makes sense because money goes also in chunks, okay? Turns out that this is what the people working in optimization problems call a QBO problem. It's a quadratic and constrained binary optimization. And we know that this is one of those very hard problems that we find in computer science. In physics, we can rewrite it using a different set of variables that are called spin variables. And it turns out that this is the typical energy function of a spin glass. And this is a quantum material. This is actually a piece of magnet, okay? This is the energy function that is describing some crazy magnet, okay? And we know in physics that finding the lowest energy configuration of this material is actually an NP-hard problem. It means that, we don't know of an efficient classical algorithm that can solve this problem in polynomial time, okay? So it's extremely hard. So solving this optimization problem for portfolio optimization is as hard as the hardest optimization problems that we know. Now we throw this into a quantum computer, in particular on the D-Wave, and together with BBVA, which is one of the top banks here in Spain, I think in the world is a top 40 bank, we did portfolio optimization for real data, in particular for 52 assets over 8 years. You can find the paper also on the archive. And we also did a benchmark of different quantum computing architectures, in particular D-Wave and also IBM Q using variational quantum eigensolvers, and also quantum-inspired methods such as tensor networks. I will not go too much into how we did this. The idea is that we built different data sets, okay, of increasing size in order to be able to benchmark different methods. We went up to a total number of qubits that was 1,272, but I have to say that we could go to much bigger systems also. And at the end of the day, this is the type of results that we obtained. For some methods, we were only able to deal with very small data sets. This is what happened with, say, IBM Q, for instance. We didn't have too many qubits at our disposal. Exhaustive solver is just brute force. Gecko is a Python solver. We went up to this data set, Excel, but for the largest ones, we were only able to solve it using either D-Wave hybrid, okay, which is a hybrid approach between classical and quantum, and also quantum-inspired tensor networks. We got very good results, very large profits, Sharpe ratio, which is another type of measure of how good your portfolio is. And also the runtimes were very good. So in particular, D-Wave was extremely fast, okay? These were our conclusions. So D-Wave hybrid and tensor networks, they were by far the best. D-Wave was extremely fast. Quantum-inspired tensor networks are very promising because this was a very preliminary version of a tensor network algorithm solving this problem. By now, we have much better tools, and we know the runtimes in particular, we know how to improve them by several orders of magnitude, and we have already improved them, by the way. And also, well, our observation was that current gate-based quantum computers were still a bit limited for this type of problem. Now, the important thing about this study is that this was the largest portfolio optimization until that point, okay, using quantum and quantum-inspired methods. And it was dealing with real data. So it was not a toy model. This was real data that the bank gave us from 8 years of a number of assets that they were trading. And we were able to fit that into the actual quantum hardware. All right. So this was, in our opinion, very promising. We also did a similar project with another Spanish bank, this time with Bankia, who is fusing with another bank here in Spain that is called CaixaBank. So in a few months, it's going to be one of the biggest banks in Spain. Also in Europe, this is also published in another article. Here, the optimization was very similar, but this time there were no transaction costs, but there was an extra constraint that had to do with a minimal holding period. It means that when you do an investment, you keep that investment for a fixed amount of time and you cannot move it during that time. All right. This constraint was very complicated to put in terms of equations, but we managed to devise an algorithm, also implemented it. And it was again using D-Wave and post-selection, which was a strategy that we, that we devised. And actually the results were fantastic. Well, this is an idea of how this post-selection worked, all right? But I want to jump into the results because they were very spectacular. So this is a plot that is kind of summarizing everything. This is a plot of the results where we are plotting the profit that we obtained for a portfolio trajectory over a period of time versus the risk, okay, which is measured by this quantity, which is called the volatility, right? Now, Bankia had different packages for their clients in terms of risk. How much risk do you want? Do you want a 5% risk, a 10%, a 50%, and so on? So the more risk you are admitting, the higher could be your returns, but also your losses, okay? Now, for the typical random portfolios, this is this cloud that one gets here. Now, Bankia was offering results that were around 20% at most during that year. This was a very good year, by the way. This was 50 assets over 1 year, also real data. And this was a very good year. I think this was 2019, where everything was going really well. And the typical, the best performance was, if I remember well, was around 20%. Now, using D-Wave, we were actually, and our strategy, we were actually able to find this trajectory up here, which is called the efficient frontier of the portfolio space, which gives you the optimal portfolio for a given volatility. And this is an extremely difficult task to compute with, actually they were not able to compute it with their tools, and using D-Wave, we managed to compute it. I mean, there are sometimes it's quite dramatic. So for instance, for around a 50% volatility, we were able to multiply by 3 the returns. So this was using the quantum computer. So this means that, there is something that this is very remarkable. This is really working very well. This is an example of an actual portfolio over 1 year. So I think it was for this point that I was mentioning before, the one with 15% risk. This is the actual trajectory. How much do I have to invest every single day of that year on each one of these assets, which in the end, we're able to boil it down to just 6, okay? And this was giving almost a 60% return. This was computed with a quantum computer. And it was so nice that the guys in D-Wave actually very recently, I think it was yesterday or 2 days ago, they did a kind of a case study of these results with BBVA and Bankia, because it was one of the first occasion in which one did a very intense portfolio optimization using real data. Okay, this was not toy model, this was real data. So this could be an actual product that you go and buy in the bank. All right, let me move on. I want to tell you very briefly about a non-typical example of an optimization problem that we also solved with a quantum computer, and this has to do with the simulation of the economy. All right, this is about predicting financial crashes. I know it sounds a bit like science fiction, but actually, one can map this problem also to an optimization problem. All right. The idea is very simple. So we have a huge financial network of many constituents. There are companies, there are clients, there are people, and then there are some assets, okay? And people have a part of these assets, and the assets have a price, and then also the companies, they own a part of themselves, and they also own part of other companies and so on. So one can put all this mathematically inside a graph, all right? I will not do that here. The idea is that at the end of the day, one can map this graph to an equation, which is an stability equation for the graph, all right? Now, if you are interested into knowing what does this equation mean, I recommend you to have a look at the paper that I will show you later, or just contact me if you want. But the idea is that there is a concept called financial equilibrium where everybody is happy, that amounts to having a minimum of a given function. And in this case, it's some cost function that is this one that is given here on the left-hand side. Now, if you are away from equilibrium, you are not in the minimum of the function. So the question here about financial crashes is, okay, let's imagine that we have an equilibrium condition, And now comes the Central European Bank, for instance, and they introduce a new regulatory measure, and suddenly the prices of some assets change by a little bit. Now the question is this gonna create a crash in the overall economy, or is the network still gonna stay stable? Well, it turns out that determining what is going to happen is also an NP-hard problem, because it amounts to finding the ground state, or say the lowest configurational state of this financial network. And this is also proven to be NP-hard, which means that this is among the hardest computational problems that we know of in computer science. In practice, it's again as hard as finding the lowest energy configuration of a magnetic system in physics. And we know that, well, this is one of the hardest problems we know of, and it's a very complicated thing. Now, what we did was to map this problem to the language of quantum annealing, and in particular in terms of bits and qubits. And it's again a quadratic and constrained binary optimization problem. One can throw this into a quantum annealer, and in practice, it should be possible for a given financial network to determine the equilibrium condition, and therefore determine whether, for small variations of the network, whether there's going to be a sudden change in the behavior of the network, and therefore a crash or not. Okay, here is here is the paper that I was mentioning. So this is not science fiction. Here is where we do the actual mapping, and here is an example where, for a very small network, okay, where you can see the transition that has been going on. So here in the vertical axis is the number of failures for a very small network. I think it was with 10 institutions, as a function of the some perturbation that we introduce. And you know, when the perturbation is very small, nobody fails. But at some point, there is a region here where if I just do a very small change, suddenly everybody fails. Okay, and it's a crash situation. All right. Now, being able to determine whether this small change that I'm introducing will keep things stable or will lead everybody to a crash is a hard computational problem. All right. Well, we simulated, we proposed how to solve this with a quantum annealer, and we also simulated it for a very small network of 3 assets. This was with the old D-Wave processor, and also with some, 3 assets, with 3 institutions, and the simulation was very successful. Nowadays, we are enlarging the size of the system. We know several tricks to do this, and we're actually, thinking about different algorithms in order to improve the simulation, but we are working towards being able to simulate, at least for a small financial network, simulating this type of situations. And the small financial networks, in some situations, may also be interesting, okay? Because if you want to consider in a financial network everybody, then the financial network is huge. But if you want to consider just, the 10 most important European banks, then the financial network is not so large, okay? Excellent. Now, in the last 10, 12 minutes that I have, let me go very quickly through 2 other applications of quantum computing in finance. One is quantum machine learning. So for quantum machine learning, there are many algorithms that people have been proposing over the years, and this is still a field of very intensive research. There is a huge list of proposals and methods, each one with different speedups. They go from quadratic speedups to exponential speedups. Here is a summary of the different, some of the speedups that you find in some of the algorithms that people have been proposing so far. You can take a look at this very nice review in Nature from 2017. It's a bit outdated already, but I think it's a good place to start understanding what quantum machine learning is all about. Now, where can we use quantum machine learning in finance? Well, anywhere where you are using artificial intelligence nowadays, you can also use quantum machine learning. For instance, in credit scoring, in fraud detection, which is a classifier, all right? In trend prediction, predicting whether the market is going to go up or down, that's another classifier. Anti-money laundering, determining whether a given transaction by a bank is a fraudulent or not. That's also a classifier, all right? So, in many situations. So I'm not going into all the details here. I just let you choose your favorite application. Examples, without going too much into the details again, oops, sorry. First one is classification. I don't have to explain you this example. Applications in finance, a lot. Fraud detection, credit fraud detection, anti-money laundering, trend detection, all this that I was mentioning. There are quantum classifiers that are more efficient than classical classifiers. Here I'm mentioning a couple of examples, but I have to say that these are quite old. And nowadays, people are developing many new quantum classification algorithms that work very well, both with quantum annealing, with quantum gate models, and some of them are based on something called variational quantum circuits also. So this is a very intensive field of research, and I think that there are very promising results here. Also, regression. So, you know, fitting a line to a set of points. It turns out that at the end of the day, we have to manipulate some data matrix, and this manipulation can be done more efficiently using quantum computers than using classical computers with something called the HHL algorithm, which is another story. But the idea is that we can do regression exponentially faster, okay? If we can have access to some way of loading the data in a quantum computer. Also, principal component analysis that has to do with finding the most important trends in a matrix of data, essentially. This is a complicated, there are classical algorithms for this, but it turns out that there are also quantum proposals, more than one actually, and a priori they are able to provide you with the principal components of a data matrix much more efficiently than a classical computer, in some cases even exponentially fast. And yeah, and so on. Now, the last example I want to mention is quantum amplitude estimation. This has to do with Monte Carlo methods. The idea here is technically complicated, but intuitively very simple. So Monte Carlo sampling has to do with evaluating expectation values of quantities that are sampled according to some probability distribution. So for instance, in finance, we have random paths of prices and assets of prices of stocks, let's say, or of derivatives. And we want to sample over all these random paths in order to find the mean and the variance and, you know, the expected behavior of what's going to be the behavior in, I don't know, in 20 years. So, so this is done with Monte Carlo methods. Monte Carlo methods are used in science everywhere, all right? Well, now it turns out that with quantum computing, there is something, an algorithm called quantum amplitude estimation that can be used to accelerate this by a square root. So whenever Monte Carlo takes 10,000 steps, quantum amplitude estimation is going to take 100, okay? So it's an important speed up, all right? So at the end of this is what I want to signify with this. So whenever we have some Monte Carlo that has to do with random probability distributions, we can map this into some type of quantum circuit, such as the one that is right here, that allows us to estimate quantities that have to do with probability distributions, expectation values, variances, and so on. Now, a relevant example in finance, both for quantum machine learning and quantum amplitude estimation, is the pricing of derivatives. This is a very important problem in finance. It has to do, the market here is huge. It's all about finding, you know, derivatives are complicated financial objects that they have a price, and this price is based on the performance of some underlying assets, okay? Now, a very important problem in finance is to know, to forecast what's gonna be the price of these objects in the future. And for this, people have different theories here. There is something called the Black-Scholes-Merton model that is a set of partial differential equations. They can be improved using quantum simulations and also using quantum machine learning. People also do Monte Carlo simulations here. So people doing quantitative finance, they do a lot these Monte Carlo simulations for pricing of derivatives by sampling paths with different, according to some given probability distribution that is given. This can be improved using quantum amplitude estimation, or using principal component analysis also to detect the most probable trends in the data to predict what's going to be the price of the derivative in the future. So again, this can be improved using quantum machine learning. Let me show you a couple of examples using quantum amplitude estimation and quantum machine learning for pricing derivatives in real life situations. Again, one is this one provided by a very nice paper by Reventros, Gupta, and Bromley from 3 years ago already. This was for something called European and Asian options, which is a type of derivative. And here, it was kind of a toy model, but they ran the simulations on actual quantum hardware on IBM-Q, and they were able to see that the convergence of the quantum algorithm was quadratically faster than that of the classical system using classical Monte Carlo sampling. Now, another option was to use quantum principal component analysis. It had to do with running a complicated quantum circuit, actually. And this is something that we did together with collaborators from Bilbao. We ran this on quantum hardware from IBM-Q with 5 qubits. And well, it was a bit noisy, but more or less we managed to do it as well. So this approach is also valid. And I think that nowadays we also know how to improve it. All right. So yeah, so pricing of derivatives is a typical example that one could also do with a quantum computer, and in particular by improving Monte Carlo sampling or using other quantum machine learning techniques. Now, there are many other problems in finance where one could apply quantum computing. If you are interested or want to start having a look into this, I recommend you this overview that we wrote already 2-3 years ago. Time flies. It's a good place to start. This was an overview by the time that we wrote the overview. And since we wrote the overview, the development has been exponential. So there are many recent developments that we are missing in this paper, but I think this is a good place to have a look, okay, if you want to learn more about the topic. And well, this is the outlook and the end of my talk. I hope to have convinced you that one can apply quantum computing to finance. We can do it. We can start to doing it already with real data and real problems. Also, there is something called quantum-inspired methods that are also useful. And yeah, so I see that Paul is already here. So thank you very much for your attention.
Roman, that was absolutely amazing presentation. Thank you very much for that. And I would say thanks for making it very accessible, and also the very concrete examples that you gave. Absolutely fantastic. I know that we've got some questions already for you. So if we can I'll just pull one or two of them up. So James is asking, he said he's doing research and looking to learn whether any companies in the financial sector are leveraging quantum technologies for storage or transmission of sensitive data. My focus is active use in a live production environment versus testing, POC, or other non-production activities. Any thoughts on that one?
For storage and transmission of data, of sensible data. No? So,
of storage or transmission of sensitive data.
Sensitive data, yeah. Well, well, for transmission of data, well, you know, there is something called quantum cryptography. Actually, that it's of commercial value already. So it doesn't have to do with the quantum algorithms that I explained, but this is another application of quantum technologies, which is how to codify and transmit information in an unconditionally secure way. Because, you know, the cryptographic systems that we have nowadays, I just explained you how to crack them, okay? using Shor's factorization algorithms and variations, no? But yeah, using quantum cryptography for transmission of sensitive data could be an option. And that's actually a technology that is already being deployed. There are companies such as ID Quantique in Geneva. There is also another company in the US, and now I forgot the name. But there are already people who are implementing this. Okay, and this is technology that is easier to implement than an actual fully purposed quantum computer, because it's you know, it runs on fiber optics, on optical fiber, and so on. Now for storage, it's a bit more complicated because storage of quantum information is complex. One has to build quantum memories. And there are many theoretical proposals to build robust quantum memories, robust to noise, all right? There are things called, for instance, topological quantum memories. There are models called the toric code and so on that we in physics, we are dealing with all the time, that they are at least theory proposals to build robust quantum memories in the lab. Some of them have been built, but only at very small scale, as far as I know. So I think this is something to keep an eye on. Yeah.
Thanks, Roman. And Tamas asks, do you expect that IBM's 1,000-qubit quantum computer in 2023 can compete with D-Wave and TN results on big portfolios?
1,000 qubits in 2023. That's they have 2 years to build 1,000 qubits. So if they manage 1,000 qubits, of course, and actually it's going to be perhaps. I mean, if these 1,000 qubits are really working, and the noise level is small, the gate error is also very small, and so on, then that could, of course, that will be the quantum computer of choice. So if you have 1,000 fully working and error-free qubits with a very large quantum volume, that's a different error measure that it's important to take into account. Not just how much, not just how many qubits do you have, but also how big is the quantum circuit that you can do. All right. Then of course that's going to be a super useful quantum computer. But I don't know. Maybe 1,000 is too much for 2 years. In 2 years' time. So.
Very
but
ambitious.
if there is somebody, it's very ambitious, yeah. So if there is somebody from IBM here, maybe they can correct. But I will say, yeah, it's very ambitious.
That's great. We haven't got the name of this next attendee, but the question is, would the active use of quantum computing in finance put more socio-economic power and particular power to further manipulate markets and therefore society in the hands of the few, i.e. the hedge funds? I think we've been seeing a lot in the press, haven't we, about this kind of manipulation in recent.
That's a very important question. Yeah. So that's why there should be an ethics commission running, determining who can use these machines for what, because yeah, I mean, as you can see, so you can use quantum computers for solving problems and manipulate and making predictions that you cannot do with other tools. It implies that whoever can have access to these machines is going to have an advantage, okay? And we need to certify that this is going to be used for, for improving lives of people and not the other way around, okay? So this is kind of a Manhattan project. We need to really have some type of ethics commission behind all this. Yeah. So I would like to think that this is going to be controlled. Okay.
Yeah, I mean, just a question for me there really is, I mean, a lot of these groups are being set up in machine learning and artificial intelligence. And but do you see, are they already being set up in quantum computing? Are they these type of ethics groups?
I know there are a couple of ethics groups that I've seen. I mean, there is also there is, for instance, this group on quantum ethics, precisely from the Quantum Wall Association.
Yeah.
Which is this, this non-profit association they have they're in Barcelona, and they involve many people, and actually one of the they have different commissions, and actually one of the commissions is about quantum ethics, and I think that their purpose is precisely this one. There are also some people from the World Economic Forum. I think that they have some sort of commissions of physicists, also economists, and so on, that they are trying to keep an eye on what are the developments and establishing some rules of good practice, let's say. So, yeah.
Yeah, thanks for that. Question from Tamas again. In your opinion, will it be gate-based quantum computers or quantum annealers that will first reach quantum advantage?
Well, it depends on who you ask. If you ask Google, I think they will say quantum gate models. Because they claim quantum supremacy or quantum advantage. So they claim quantum advantage 1.5 years ago. I think, even though nowadays this is a bit unclear. I don't know. I think the people are putting a lot of effort into universal quantum computing gate models, and I think that these are going to be the first ones to achieve really proven quantum advantage. Let's say. That doesn't mean that that quantum annealers are not useful. The problem with quantum annealing, at least in the way in which we have it right now, is that it's not coherent, in the sense that it's not happening really at zero temperature, and we know that there are quantum effects going on there. The machine is super fast. We can use it, and it's giving solutions that are certainly very good, but it's difficult to certify. Okay. On the other hand, with gate-based models, this is easier, and one can actually devise problems that are built exactly for this. Such as, I mean, this quantum advantage claimed by Google, it wasn't a problem that was entirely academic. This was, sampling of random unitaries. This is something that a priori is built for a quantum computer. Okay, so I think for proving quantum advantage, I think it's going to be, I think quantum gate-based quantum computing has more possibilities.
Thanks, Roman. I think I know the answer to this one, but are there any essential differences between classical and quantum computing except for the speed of calculation? I'm wondering if classical computing could solve the same problem without a time constraint, or there exists structural difference between them.
No, well, I mean, it's not just time. It's time. It's the way they process information. Okay, so for instance, let's imagine 1 qubit. This is an interesting difference. So let's compare 1 bit versus 1 qubit. In 1 bit, you just have two values, 0 or 1. Okay, if you have 10 bits, you have 2 to the 10 possible values. Okay, so everything is digital, it's discretized. So you cannot represent real variables. Okay, you cannot represent the square root of pi with infinitely many digits. You cannot. You have a cut down in precision given by your number of bits. Okay. Now, if you pick up 1 qubit, it can be in 0, in 1, or it's a vector. Okay, so it can have any superposition. So it could be easily be in the square root of pi 0 plus 1 minus I 1. Okay, so you have real variables inside of a qubit, and this gives you an infinite power of representability, let's say, that you don't have with a classical computer, at least the ones that are digital. Okay, so from that point of view, even if you use qubits to discretize quantum information, the qubit itself is not discrete. All right, so it's manipulating information in a very different way. Now, at the end of the day, the difference that we see in practice is the speed up. We can manipulate information more efficiently. Therefore, we have faster algorithms. What we are seeing now in quantum machine learning is that sometimes they are also more precise. Okay, so even perhaps for the same amount of time, running a neural network for 10 days or running a variational quantum circuit for 10 days, the variational quantum circuit gives you better results in the sense that it's able to detect anomalies more precisely and so on. Yeah. So yeah, those are the advantages.
That's great. Roman, there's a whole bunch of questions about the access to the links of the cited papers, etc. I think you put the links in the presentation, didn't you? And the presentation is all being recorded, so yeah. So this will all become available to people. Yeah.
Yeah, I'm also going to share the slides. So.
And I know there's a discussion going on in the chat. I can't follow it all at once, so I can't multitask. But I think some of the links are being shared there as well. There's a question about are the systems compliant with GDPR? I guess that just depends on how you use them, doesn't it?
How you use what? Sorry.
So are the systems compliant with GDPR? But I guess that's the data protection regulations.
That depends on how well
what you put in and what you take out. What you put in.
You should make them compliant. Yes. In our case, I mean, for instance, for the case of the pilot projects that we did with these 2 banks, the data was public. Okay. And therefore there was no particular problem with that. But for instance, if you want to run a tax fraud problem, okay, or something like this, so typically data is anonymized or is encrypted, and this is how you have to. I mean, if you take into account that so far quantum computers are running mostly in the cloud. It's not that we are buying a D-Wave machine and we have it here. So if you have to send the data there and then process it and then it comes back, everything has to be either encrypted or anonymized or
I'm guessing, Roman, that most of what's being done at the moment are effectively pilots, aren't they, rather than production systems?
Yeah, mostly yes. Even though there are some banks that already they are starting slowly to put things into production.
Yeah, I guess some of the banks, given the results you're getting, I guess some of the banks would like to get them into production fairly quickly, right?
Yeah.
Must be pushing for it. Okay. Is it possible quantum internet based on non-locality? So is it possible? I guess is it possible to have a quantum internet based on non-locality?
Yeah. The answer is yes.
Okay. The answer is yes to that one.
There is even a very large effort here in Europe to build a quantum internet. So there is an initiative here that is called the Quantum Flagship, and many projects in this Quantum Flagship went to quantum communications to build things like the quantum internet, so quantum networks.
Yeah. I mean, how does that relate to the rest of what you've been talking about? Because quantum internet is another thing altogether, isn't it? Presumably that.
Yeah. It's a completely. So quantum technologies they are very broad. It's about using quantum mechanics to process information, and that has to do with computation, with communications, with cryptography. Each one of them is a separate field. Okay, they are all related, but yeah. So.
Yeah, Lewis is asking a question. I don't know Tufi Salibar. Apparently he's or she has suggested an ethical layer for blockchain. Have you come across any crossovers between quantum and blockchain in terms of this sort of thing?
Yeah, well, quantum and blockchain, I think I know of some papers that actually they are proposing either blockchain schemes that are robust against quantum attacks. Okay, that means attacks by a quantum computer, or that they are using directly qubits. Okay.
Yeah, I think Lewis is more suggesting that they've come up with an ethical layer.
No, not yet.
Yeah, but not in quantum, right?
Not yet.
No.
I know people are exploring that, but not
yet. SK is asking whether you can talk a little bit more about yourself. Are you spending time in both academia and industry? It looks like it. Or your company is driving these research and publish them. Are there some low-hanging ideas you're looking at currently? I'm guessing most of the case studies you've discussed are the low-hanging fruit, and I guess that is for the company rather than academia, is it? But
yeah, well, I'm doing a superposition actually. So yeah, I'm doing both things at the same time. So I'm running a research group at the DIPC on tensor network simulation methods for quantum many-body systems, but that has to do more with more physically oriented problems such as quantum materials, quantum states of matter, and so on. And then the company, which is about quantum computing for finance, which is a different story. Nevertheless, both things, they are not totally independent to each other. They reverberate, and there is a close connection between the two. Okay. Now about long-hanging fruits, well, it depends. Depends on what you understand about that. Yeah, there are problems that they look closer than others, and the ones that have to do with quantum optimization of quantum machine learning. Yeah.
Yeah, the low-hanging fruits in quantum are a bit higher than the low-hanging fruits elsewhere.
Maybe.
But yeah, I'm really interested in what you were saying about academia and the fact that you are doing a startup. I mean, my area of, I should have said at the beginning, my area of interest really is working with startups and entrepreneurship, and I run some accelerators in areas like drug discovery, for example, the AI drug discovery. But I know that in deep tech there is this very close relationship between academia and doing a startup, because you have to have the knowledge in the first place, right?
Yeah.
To do this sort of thing.
Absolutely, yeah.
So that's really interesting. There's, I guess, Michelle is asking a question again about ethics and GDPR, and about the explainability of results. I know this is a question that always comes up with machine learning and AI, really, isn't it? And I guess, is it similar with quantum?
It's exactly the same. there is no difference. So there are algorithms. For instance, there are some algorithms such as in typical AI. So if you have a classifier, if you have a neural network, the explainability is very difficult. But if you have another type of classifiers, say support vector machines, for instance, then this is much better. So in quantum, it's exactly the same. So if you do quantum neural networks, for instance, or variational quantum circuits, this is very difficult to explain. Why the result is as it is? Well, we know more or less what is happening, but there is no way of understanding it clearly. But for other algorithms, it's quantum support vector machines, quantum decision trees, and so on, explainability is much better. So the situation is exactly the same as in classical ML.
Thanks. And I honestly ask the very obvious question, which I guess a lot of people would be thinking is, what about using quantum computers for crypto mining? Is this possible? There must be a lot of people thinking that.
Maybe. But it has to be complicated to make a farm of quantum computers. But yeah, why not? I mean, I don't see a reason why it shouldn't be possible.
Yeah, it's an interesting application, I guess. Lewis has just given some reference to the network we were talking about earlier, the ethics network there. So if anybody, just for reference, it's TODA.network. So TODA.network. If anybody wants to have a look at that later on. Right. I think at the moment this is the final question, but please do continue to ask if you have any more. Michael Kirk asked, no, I think we've done that one as well. That was about the ethics and things like that. So does anybody have any more questions? Please continue to put them there. But if you haven't, I'm going to just ask one on behalf of my son, which I always do. Roman, I think my son may have taught you. He's done a quantum MSc in quantum technologies at UCL, and I think he's got a problem that a lot of people might have, that he's, even with an MSc in quantum technologies, he's still slightly underqualified for a lot of the quantum world. A lot of people are demanding PhDs. Do you think this is still a domain where you really have to be a PhD to, for example, quantum startup? Or
I mean, I will say the more you have, the better. Okay, of course, but yeah, well, look here in the company. So in Multiverse, we are hiring many PhDs, of course, but we are also hiring people with a master. So actually, some people that came here without the PhD, they are doing the PhD here with us now. So yeah. So I will say that no. So at this moment, so quantum startups especially, they need a wide variety of skills. And I will say that there is room also for people without PhD, as long as they have a solid background on some key topics of quantum.
Yeah. That's the use. I'll tell him to keep trying harder then, and get a few job applications in. So yeah, thanks for the advice. I guess the other area I'd like to ask on behalf of the audience is really about startups, entrepreneurship. Do you have any tips for how to make the jump from, say, academia into doing a deep tech startup? I'd like to help myself as well. I do these accelerator programs, but it would be useful to get your sort of feel for something that has a very kind of slow burn, to the use cases. Like it's a bit different from a lot of startup environment, right?
Yeah, I think in our case, what made really the difference, and I think this was something that was, for us, it was definitely very important, is that the founding thing of the startup was really very balanced. So let's say there was something with a very strong scientific background. In that case, it was me, okay? But then there was another of the founders, he has a very strong financial background. He was the director of a bank, actually, in Spain. So, and also a very strong business background. So he knew how to, go to the banks and tell them, well, look, this is the problem that you have, blah, blah, blah. And then he came to me and translated that into the language that I could understand. And then we translated back and forth. This was absolutely fundamental, because if if I had to go directly to the people in banks and explain them what I could do for them, they would have never understood me, you know, and also the other way around. So the people, you know, we speak different languages, and it's important to have a very balanced team that they really know how to talk to each other. And for us, this was very important to have somebody with a very strong technical background that knew really about the technology and how to solve the problems and so on, and also somebody who knew how to talk to the actual clients. Okay, so, and who knew about the key problems in the market that we could solve, because we need to know. I mean, in a startup, we need to provide something that is of value, no? And at the end of the day, we need to be solving problems that the clients are going to be interested in, they want to buy, and so on. And there must be somebody that understands also that, okay, that really reads the necessity of the market. No? And for us, that was one of the keys, that we had a really strong and very balanced founding team. Okay.
Yeah, and by the way, everybody, that's a fantastic bit of advice. I mean, if you are thinking about doing a startup, and actually in any field really, team is probably the absolute #1 thing that you need to, you know, get sorted out fairly early on, to make yourselves investable, and really to, you know, to push ahead, because it's very, very hard to do most of these things, you know, on your own. It's quite a lonely journey, right? Doing a startup, you know, even with a team around.
Yeah, yeah, it's a full-time job almost. Yeah, I mean, you spend many hours doing things that you will never imagine. Yeah, so, yeah.
Well, that was fantastic. Roman, I think that's we've got through quite a lot of questions there, and it's great that, you know, people were so interactive, and, you know, thanks for giving your time as well. As I say, fantastic presentation and very accessible. I think, you know, people will have learned a huge amount. I know I certainly have. So I'd really like to thank you for your contribution today. I'm just going to put up a final slide. If we were able to, I'm sure we'd give you a big round of applause, but I think you're just going to have to put up just to me doing it this time. But I'm sure people enjoyed it greatly. So I'm just going to put up the something here to. Yeah, so everybody, I'll keep this slide up while I just sort of do the final wrap up. This is the next event on the 26th of March, Quantum Computing for Agriculture, Efficiency and Sustainability. From my point of view, you know, I'm looking really for some collabs over the next year. And particularly in areas of, you know, anybody who wants to do a startup in quantum, please make contact. I put my details on the chat. I'm very happy to help through some of the accelerator programs that I'm running, and through some of the ones that I'm planning to run. So please do reach out on that side. But thanks, I'd like to thank once again, Roman, for, as I say, a great presentation, and thank you for being such a great audience, and you know, and being so proactive and interacting. So I hope you all have a good evening, if it is evening with you. I think it is with most of us, and look forward to seeing you at the next event. Thank you very much.
Thank you.
Bye, guys.